Okay, so here's a video for class 6. We are moving on to chapter 4 of Sengel, and we're going to look at fluid kinematics. Today we're going to talk about flow visualization. And so some topics I've brought up before, mentioned the idea between the Lagrangian perspective that we have over here on the right-hand side and the Eulerian perspective, or Eulerian method and Lagrangian method on the left-hand side. On the right-hand side is what we usually think of. In most cases, we take a look at a particle and we follow that particle along. That's what we did in dynamics. But now in fluid mechanics, it becomes because we have so many particles, instead of following all of the particles, we draw a little control volume in space, and we watch the particles move through them. And that's a different perspective, and we're going to see that we're going to need to do some things to try to make those things connected. We're also going to describe some things, and a lot of this is just sort of introducing a bunch of flow ideas. So as a concept, we're going to talk about the velocity field. Much of fluid mechanics, and particularly fluid kinematics, deals with trying to describe the flow, and in order to do that, we really need the velocity to be described fully. So that velocity field concept is something we're going to be looking at. We're also going to introduce this idea of streamlines. It's another way to view how particles together are going to be flowing and moving. And so to be able to systematically approach this thing, we're going to create streamlines. We'll also notice there's something called velocity potential. I'm not going to cover that really, but this is like sort of an old school way and maybe a higher math way of trying to describe a flow field. There's also, we're going to talk about and just introduce, and all of this is just introductory stuff that we're not going to use for a while, but it's a good time maybe to put it all into perspective. There's something called irrotational flow, and we'll try to see, and that really applies to vortices. So we'll see that coming up soon. And then maybe I'll just mention quickly something I jokingly have with this picture of superposition. But the idea that sometimes when we want to really describe a flow, what we could do is we could take some fundamental flows that we know and add them together to create an approximation of the flow we want to find. And we could do that with any kind of linear system that we use superposition. But I made the joke that he's standing in his superposition. Isn't that funny? Yes. Okay, so here's some pretty pictures, reiterating some stuff I already mentioned about the Lagrangian method is to pick a particle and follow it along, like if there's smoke coming out of the stack, maybe, right? So there's some kind of exhaust stack coming up, and we would take a look at that particle. But instead, maybe we want to take a look at a particular location and track as particles go by that. Or even like a control volume we might want to have and draw and see how the numerous particles are entering and exiting. So that's the Eulerian method, and it's well suited for fluid flow as compared to Lagrangian method, which is better for like maybe a solid object that's moving. Just noteworthy, we do a little weird thing in fluid mechanics for some reason. Instead of using the component symbols, it's very common for a velocity vector to be described as having this lowercase u for the x component, lowercase v for the y component, and lowercase w for the k component. So we're going to try to get used to that. And a three-dimensional velocity field is very difficult to try to get your head wrapped around. So most of the time we'll use a two-dimensional, and sometimes if we need to really kind of zoom in and try to understand a concept, we might use a one-dimensional here, where we're going to use this u. We also want to introduce this idea of steady and unsteady flows. And that isn't necessarily what you're seeing here. Is we're seeing the partial derivative of velocity with respect to time. If that equals 0, then we're going to call that a steady flow. That doesn't mean there's no acceleration. We'll see that soon. This is the partial derivative with respect to time, because velocity can change with respect to position and location, that is. And so we can actually have acceleration even though we're under the steady flow. We'll go back and look at some of those pictures we had from maybe the first class, where we had, like, for instance, having that still shot of a waterfall where you can see there's just this chaotic random motion, but we can actually make it, and that's going to be unsteady, because if you go to any one particular position, something's going to be different in time. But if you were to take the approximation, which is really what you're doing when you're not taking the super high speed shot, but you just take a snapshot that actually kind of develops over some time, you can kind of have an approximation of a steady condition, perhaps. So this velocity field is kind of hard to wrap your head around at first, but I think we can do a couple examples and it can kind of make a little bit more sense. So this idea of a field representation is that we can imagine perhaps a room, or maybe just a lot of times it's better to imagine a two-dimensional thing, and you can imagine a whole bunch of different locations and little spots. And if you focus in on individual spots, like you set up a little grid and you look at what is the velocity at that particular spot, that location. We did this sort of the same thing with the pressure gradient, right? If you recall the pressure gradient, we pictured all these little points in air, maybe a systematic grid, and at each of these points, we ask ourselves, what is the pressure at that point? Well, we do the same thing for the velocity, where we pick individual locations. We go, okay, what is the velocity in the x direction at this particular location? And what's the velocity in the y direction at this particular location? And the same thing with the velocity in the z direction at that particular location. So at each of those components can vary depending on what their position and the time, right? And remember that for any particular velocity magnitude at any particular position, that's going to be the square root of the sum of the components squared, which is the speed, right? So right here, I think these kind of help you to picture this thing we just described, right? If you're confused by the velocity field, I really think that taking a look at these little diagrams right here, which were, I think they're called quivers in MATLAB. That's a way of plotting out some equations that would describe a field. We could see that we have this flow going on. So the one on the left, picture this, we're looking down into a room and this is the door. And let's say some wind is coming in from the outside, and then over here we've opened a window. Now you could picture, if your desk is right here or something along those lines, or you could kind of feel the breeze coming across you in that direction. But if you were like over here instead, it might be a different type of feeling for the breeze, right? So a lot of times what we'll do is we'll draw a line over here and kind of see the track of like what a typical motion would be. And these things, I'm going to jump the gun and tell you, these are called streamlines, right? They're a way to try to describe how the motion is going on. Now, this right here, let's assume this is a picture of a steady thing. But if, like, 2 seconds later, all these arrows change direction, that's an unsteady flow. But if it maintains this kind of flow pattern right here, we could call that a steady flow. And we'll talk about this soon again, but we could have acceleration, because if we look at this spot over to this spot, there is a difference in the magnitude of the different of the components from one spot to another. So therefore, if the velocity changes in one spot to another spot, there must be acceleration. Here's another example right here. You can picture this as maybe a sink, right? So this is like a sink full of water, and we're only going to look at one level of it, and we can see these arrows, they're spinning around, right? And maybe they're making sort of a spiral thing. But once again, we could kind of like draw these and think of these as streamlines, right? As long as this is a steady operation, that is, that like this snapshot will remain true all the time, that's going to be steady flow. And by the way, this is the concept of the vortex, right? A vortice, right? That this is going to be like a sink that things are coming through. And as I mentioned with the superposition idea, sometimes we might have a flow like this and a flow like this, and we could kind of combine them to try to simulate some other flow. So that's the idea, that we could try to figure stuff out by breaking it apart or adding it together to simulate a flow. Let's see. Almost, I don't know, maybe enough. Maybe that's enough for one video for right now. Yeah, I think so, because I think I want to go to streamlines in the next video after this. So let me see. Let me take a look. Is there anything else I wanted to say here? You know, only that, like, a lot of times the flow patterns that you might see and we might create equations for are actually like just a little portion of the actual flow. So like we might have an equation right here that in this one is describing the flow field, the velocity field. But actually all we really want to do is try to quantify something in particular about like this entrance region into you know, the entering into like a pipe, right? So this is the entrance into a pipe, and we want to describe what's the pressure, well, first the velocity field that's taking place. Don't get ahead of ourselves. A lot of times, you know, remember we're in kinematics, and kinematics is just describing the flow. We don't know why it's flowing. Later on, when we do the kinetics portion, we'll have the interrelationship between pressure and these velocities, and we'll see the point of this whole thing. But that's a different time. But just mention, it's a lot of times it seems as a student you might feel it's sort of an abstraction to have an equation that describes this flow, and like, how would I ever know that it's going to be like that? Well, you know, perhaps you're not just going to get this. You know, if someone's not going to hand it to you, you're going to look at a flow and then try to go work backwards and try to describe what that flow field is like in a small portion of the field, right? You're not always going to be able to create equations that are going to be true everywhere, but maybe you can find equations that are going to be locally true. Okay, so that's going to be it. Let's seal the deal on this one.